On this worksheet, we're going to be calculating the voltage of a non-standard voltaic cell. One of the characteristics of a non-standard cell is that it has at least one solution with a concentration that is not equal to 1 molar. And in this particular case, we've got 4 solutions that are non-standard. So to calculate the voltage of a non-standard cell, we will use the Nernst equation, which says that E, which is non-standard, is equal to the voltage of the cell if it was standard minus 0.0257 over N. I'll talk about what N is in a second, times the natural log of Q. Now there are actually 2 different versions of this equation. One of them uses a log, not a natural log, and in that problem, in that equation, this number is a little bit different. So like I said, this ecell is going to be calculated the same way we would calculate for a standard cell. So this is just going to be our cathode minus our anode. This is what the voltage would be if the cell's concentrations were all 0. N is the number of moles of electrons that are being exchanged in the overall redox reaction. So when we're looking at this one right here. And then Q is our reaction quotient, which we learned about a long time ago, products over reactants raised to their stoichiometric coefficients, leaving out solids and any pure liquids that might be present. So we could start this problem in really any place that we want. Let's go ahead and start with our standard ecell calculation. To do this, we want to look at our overall reaction, and we want to find a couple of things that are going to be easy for us to locate in the table of half reactions. So we've got the table of half reactions over here we're going to use as a reference, and I've decided I'm going to begin by looking for this vanadium compound here, and it looks like all the way down here on the bottom, I think this is where I have found it, right here. It looks like it's not exactly the same as the one that's in this problem because there's some extra stuff in there. That's okay. We'll just use that. So what I'm going to do, I'm going to focus on the VO2 plus. It is on the left-hand side of my equation, and it's also on the left-hand side of the equation in the table of half reactions. Make a note on that. And then also take a look at the VO2 plus, that's on the right-hand side, same as this one. Oh, I guess I kind of glossed over this. It does say it's an unbalanced reaction. So what I'm going to do is take the half reaction from the table, and I'm going to copy it exactly the way that it is, because I don't think that, I don't know anything about if I've got to change stoichiometric coefficients or not, but I know that it's going in the right direction because I have the VO2 on the VO2 plus on the left-hand side, and that's where I need it to be. I am going to be including states, even though sometimes I leave those off, because we're calculating Q. So states are going to be an important thing to keep in mind when we're setting up our Q calculation. And also, while I'm here, I want to copy the voltage down for this particular half reaction. 0.991. The other piece of this is going to be the iron and iron 2 plus. So now I need to go locate that. And it looks like we want to be a little bit careful because it looks like there's 2. I want this one right here. I want the one that has iron 2 plus and iron not charged. I do notice that in this version, it is reversed from what we have in this reaction. Overall, we have FeS on the left-hand side. That's where we want it. But in the table, it's on the right-hand side. So we need to take this reaction from the table and turn it around. We want our we want our Fe solid on the left-hand side, and then Fe2 plus aqueous, and 2 electrons, we want that on the right-hand side. And then while we're here, let's get that voltage. The voltage is negative 0.447. Okay, now I'm going to get rid of the table of potentials. We don't need them anymore. Here's our 2 half reactions. So we can use this to calculate our ecell. Let's go ahead and do that. We do need to identify which is the oxidation and which one is the reduction. Oxidation is loss, oil rig. This is the reaction that's losing electrons. This is our oxidation. This is our reduction. Red cat tells us that this is a reaction taking place at the cathode. Here's our anode. And let's go ahead and solve for ecell. Ecell is going to be the cathode, which is 0.991 minus the anode, negative 0.447. That voltage is 0.991 minus a negative 0.447, 1.438 volts. And I am going to move this stuff down, and I'm going to put that number right here. 1.438 volts. The next thing that we want to figure out is N, the number of moles of electrons is being exchanged in the reaction. That comes from looking at this half reaction. Notice that like we did know, it took me a minute to figure out, but the overall reaction that's provided to us was not balanced, and that means when we took the equations out of the table of reduction potentials, the stoichiometric coefficients weren't just right, and we've got the wrong number or a different number of electrons in the two half reactions. The number of electrons that will fit into this particular equation is the number of electrons that we would have if we were to add these two half reactions up. If we were going to add these two half reactions up, we would want to multiply the half reaction, the vanadium half reaction, multiply everything by 2 so that we can get the correct stoichiometric coefficient. Let's just go ahead and do that. I'm going to take my voltage calculation and I am going to move it up here, and I'm going to delete these things for a second, and we're going to change the stoichiometric coefficient all the way across this particular equation, multiplying everything by 2, and then let's combine these two together. So we get 2 of the VO2 plus aqueous plus 4H plus, also aqueous, plus FeS. I'm leaving out these 2 electrons because I know they're going to cancel. On my product side, I have 2VO, 2 plus. I left that state off, but that is aqueous, plus 2H2O, liquid, plus Fe2 plus, aqueous. The number of moles of electrons that we're going to put into the Nernst equation is a 2. So let's go fill that in. 1.438 volts minus 0.0257 over 2 moles of electrons. The last thing that we need here is the natural log of Q. This equation right here is what we're going to use to come up with the expression for Q. Q is products over reactants raised to their stoichiometric coefficients. So starting with our products, we have VO2 plus, and the stoichiometric coefficient is 2. We have Fe2 plus. We also have H2O, but we leave that out because it's a liquid. For our reactants, we have VO2 plus, and its coefficient is 2. We have H plus, its coefficient is 4. And then we're going to be leaving out the Fe solid because it is not included. Solids are not included. So this is the expression that we're going to use to calculate Q. We need to get these concentrations from the problem itself. The concentration of VO2 plus up in the problem, VO2 plus is 1.38, and we'll need that to be squared. Fe2 plus is 4.09. VO2 plus is 0.496, and that needs to be squared. And then last but not least, H plus, 3.48. And that needs to be raised to the 4. So let's go ahead and do the math on this. 1.38 squared times 4.09 divided by 0.496 squared and 3.48 to the fourth. And I am getting 0.216. That is the value of Q that we want to put up here in the Nernst equation. 0.216. So now all we have to do is just solve all of this math. I'm going to leave the 1.438 volts part alone to start, and I'm just going to solve this side right here. I'm going to take the natural log of my Q, and then I'm going to multiply that by 0.0257 divided by 2. And this gives me a negative 0.0197. And then I can just finish this, 1.438 minus the negative 0.0197. This gives me a voltage of 1.458. Notice that it's not very far off from ecell standard, and that's pretty normal. They're not going to be hugely different. So that's one of the ways that you can double check that you've done this correctly, which is a good idea to do because there are so many steps in this problem. There's a lot of places where it could go wrong.